This is FE Peer Review. The date is August 30th, 2021. No more ignorance. First lesson in statics, catenary curves. This video is a follow-up to the video I posted about a week back called In Praise of Ignorance. And this video looks at the basic statics, the basic principles of forces that are on a structure. And in this case, the structure being a rope with a weight hanging on it, or in addition, a rope under its own weight. This is a great starting point for learning about the way that forces interact with structures, building structures, for example. So this will be the second of 3 parts. I had originally thought to do this just in 2 parts, but I need to go, it's going to take too long. So I'm breaking it into 3, and this is the second of 3 parts. And in the third part, we will go into more detail with the math, but in this video now, very little math. And we'll pause here for a moment, and then we'll move on. I had further conversation with just Barry, and he clarified an important point. I had a basic misunderstanding of the experiment that he's planning to do. In light of that, I had already made quite some progress on the video I was working on, and I decided to continue with my original plan for my video, but I would take a moment here to discuss what he's actually going to do versus what I thought he was going to do, and then I will append a piece to the end of this video looking at the detail of his actual intended observation. So my original assumption was that he would have, this is the water here of the tunnel, and he would have an anchorage point at one end. He'd pull a line across and then pull on it to get it straight and have an anchorage point at the other end. He could then measure the distance above the water at each end and the distance above the water in the middle. And by using those distances, come to a conclusion. So I do think that would be an interesting experiment, and we'll look at what that would involve. However, what he's actually planning to do at this point is have a buoy, an anchor at one end, pull a line right at the water line so that the line is actually on the surface of the water, not above it, and then anchor it at the other end. He has, I think he is got the idea that if the Earth is round, then the line will end up submerged when it's pulled into a straight line. If the Earth is flat, it won't. So we'll come back to that at the end of the video and look at that in more detail, but I still think it would be worthwhile to continue with the analysis as I had planned it. What we have here are 5 diagrams with possible outcomes of the experiment as I thought Barry had in mind to do it. Starting at the top, we've got an anchorage point at each end. We've got a string pulled to a perfectly straight line. And the Earth being flat, we have a flat water surface. So we have an equal distance between the string and the water at each end and in the middle. Now, if it should happen that the Earth is actually curved, then we see in the second diagram that the distance measured at the middle will be less. However, this is all based on the assumption that the string, we've succeeded in pulling the string to a perfectly straight line. There is another possibility, which is that the Earth is, in fact, flat, and that the string is sagging a little bit. That would give a very similar looking data set to the previous example. It would be quite difficult to differentiate between which of those was actually occurring, if that was the kind of data you got. The fourth diagram down here shows both a curved Earth and sag in the string, and again, same problem as with the previous 2 in terms of interpreting the data. The last thing I want to mention is a problem that will not arise with the string, but were Barry using something like a laser, which could be subject to refraction, we would potentially have this result, and I thought I'd just include it to make this analysis a little bit more generalized, because it could be applied to lasers as well. So what I've shown on the bottom diagram is a dotted line to indicate that it's a laser line rather than a string. And given that you often get a very high humidity layer in the inches or few feet just above water, it's very possible to have a phenomenon occur called atmospheric ducting, which basically keeps the light path tight to the surface of the water. In which case you would, again, possibly see the same measurements at each end and in the middle. One of the reasons why I like this idea is that he's not using a laser, and so we completely eliminate the refraction issue, which does complicate things. We've substituted a different set of problems, which have to do with sag. But at least for me anyway, wrapping my mind around sag in a line is a little bit easier than actually trying to calculate the refraction side. So those are some of the possible results. One of the reasons I thought to do this video was because it's a chance to reinforce an idea that I think Barry and others would benefit from, and that is that math, for a start, math really does have a very important role to play in organizing our daily lives and making the world around us work better for us. But at the same time, although some people may struggle with math, it's not always necessary to have the full math skills. If you have the basics, you can develop a kind of intuitive understanding of how things work, which is supported by the math. Now, you may not be able to derive all the differential equations and all of that kind of stuff, but if at least you respect what the math can contribute and you can grasp the basic ideas, then you can develop an intuitive understanding of how the world works, which is based on something substantial and not just false impressions. So I'm going to take this opportunity to introduce some basic physics concepts, and it basically all comes down to Newton's third law. This is my working career started in structural engineering, and I got a master's degree in structural engineering and worked for an engineering firm, designed a lot of large infrastructure things, water tanks, wastewater treatment plants, highway bridges, industrial buildings of various kinds. And it was all just really the most basic kind of physics coming out of Newton's three laws and his law of gravitation. That's pretty much, if you've got that, you can design just about any structure, any building structure needed. So here's a fella, and he's holding a rope, and at the end of the rope there's a weight, and it's hanging down and it's pulling the rope tight. Now if he's using a rope or a chain, these are tension structures. All they can do is transmit tension. Now there's no way he can use a rope or a chain to hold this weight off to one side of him. It's gonna swing back down underneath his hand no matter what he does. If he were using a stout stick or a steel bar, then he'd be able to hold the weight out away from him. But the bar would be bending and the stick would be bending. But with a rope or a chain, it's just going to hang straight down. So Newton's third law says that for every action, there's an equal and opposite reaction. We can take that, his hand holding the rope, holding the weight, and we can look at it in respect to Newton's third law and say, okay, the earth is pulling down on the weight. There's a downward force on the weight. There's an equal and opposite reaction pulling upward by the rope. And that's why the weight doesn't fall to the ground. Of course, if there was no rope, the weight would just fall to the ground. So if this thing is balanced, not moving, and that's what this third law is about, then the weight being pulled down to the ground is going to be counteracted by an equal and opposite reaction upward from the rope. The rope, likewise, is being pulled down by the weight at one end and is being pulled up by the person's hand at the other end. And then we can look at the hand itself, and we can see that the hand is got an equal and opposite reaction to the rope. Now, I didn't bother to get into the whole body and the feet, but it all ends up back down in the ground again. But that's not important for our exercise. If you want to follow it through, you can do that. This here is called a free body diagram in structural engineering. And it just means that you've basically taken the pieces of your structure apart and you've identified the forces that are happening where each of these pieces meet. It's a really powerful tool for analyzing structures, and actually requires no math at this stage. And I would never design a structure jumping into the math. I would always do a free body diagram first and just figure out what kind of forces are going to be happening at each of these points. And then when I understood that, only after that would I start dealing with the numbers, because it's really easy to make a mistake with the numbers yet and not know it. But if you've worked out in principle what the solution is going to look like, then when you plug the numbers in and you accidentally punch the wrong thing into your calculator, you get a number that doesn't match your original free body diagram and your original intuitive analysis, and you say, okay, something's wrong here. I didn't get the kind of result I'm expecting. You go back, you find the mistake in the math, at least I found my mistake in the math, and you fix it and you move on. So that's the power of a free body diagram. Now let's see what happens when he gets his buddy to come over and take the other end of the rope. Now, each of them is holding one end of the rope, and they can carry the weight in between them without any problem at all. The weight is way away from them, but it's being held by the rope. Now let's take a look at that as a free body diagram. We've again got the weight, and Earth is pulling it downward. That's all that's happening on the weight, is it's being pulled down by the Earth, straight down. We can call that the y-axis. We'll call horizontal the x-axis. So that weight isn't falling to the ground because the rope's pulling on it. The rope is a tension element. It can only pull in a straight line along its length. So the rope is pulling off to the upper right, and the other end of the rope is pulling off to the upper left. Likewise, the rope on the right side is being pulled by the hand in the same way, and the rope on the left side is being pulled by the hand. So now we've got our free body diagram worked out for this shape with the rope and the weight. And by the way, anything that's a truss, like a roof truss on a house or trusses on bridges, definition of a truss is basically a bunch of triangulated shapes. There are other kinds that involve rectangles that are not, strictly speaking, trusses, but they're sometimes called trusses. But trusses basically are built out of triangles. And when you do that, you end up with only having tension or compression elements. And what we have here with the rope are basically two tension elements. It's one rope, but it's like acting like in two pieces. So what I've done here is I've taken our free body diagram to the next step. And I've taken each of these little angled black arrows and broken it down into a vertical component and a horizontal component. We can say that if the rope is pulling to the upper right, then it's pulling somewhat to the right and somewhat upward. So that's what the two colored arrows represent. The green is the amount that it's pulling to the right, and the red is the amount that it's pulling up. So at each angled arrow, we see these red and green versions. And if we go back to Newton's third law, equal and opposite reaction, we'll go up to the guy's hand here. The red is the equal and opposite reaction to the red at the end of the rope, and the green at the end of the rope is the equal and opposite reaction of the green at his hand. Let's look at what happens when we have different angles on the rope. Here we've got the two guys with their hands quite close together, and the rope and the weight is hanging almost straight down. The angle of the rope is very steep, and if you look at the red and the green arrows, we've got the red arrow. These two red arrows are equal to the weight pulling down. And because of the steep angle, there's only a little bit of a sideways force involved on the rope. So the green arrows are very small. The same applies at the top end of the rope. Because of the angle of the rope, almost all of the force of the weight is being resisted by the vertical component of this rope here, which is the red, with the horizontal, the green, being very small. Now the bottom diagram shows the kind of the reverse situation. We've got the rope being pulled very tight. We've got the weight being pulled down, and it's resisted by these two little red arrows here. But because the rope is at such a steep angle, the green side, the green component, is much larger than the red component. So you can see this green force could be even bigger than the weight itself. One way to imagine this is to use the idea of a lever. We are all familiar with a lever. We've got a guy here, and he's got this long distance, and using this long distance of his lever arm, he can lift the stone because this end of the lever is short. So he's able to lift a very heavy stone because this piece is very short compared to that piece. If we look at this diagram at the bottom again, we see that the weight has got a big advantage over the hands. It's got the lever working for it or against the hands because the weight is way out from the hands, pulling this long distance, just like this guy is using the lever with this long arm. And the hands, they only have a small distance to resist with. So they're like the poor guy at the opposite, flipping his lever around and looking at it from the opposite end. So that's a way maybe to help conceptualize a little bit why the weight way out here could cause a force on this rope that's much higher than the weight itself. Now that we've got the idea about the way the forces move through the rope, let's look at a situation with two weights on that rope. We have two weights equally spaced. We've got the two guys at each end, and this is the way your rope would hang with these two weights on it. You can break this down into a free body diagram, and you'll see that indeed everything balances out and everything has its own equal and opposite reaction all the way across. You can repeat that same exercise with three weights on the rope, and it will take on a shape something like this. If you pull the rope tight with three weights on it, you'll have this configuration, which will be similar to the rope that was very tight. Let's see, that was this one down here, but with three weights. Finally, you can imagine that the rope itself is heavy. It's a whole bunch of little weights all the way across. And if you do that with the rope having its own weight, the shape that it takes, that's called the catenary curve. Sometimes it's mistakenly thought to be a parabola. There's a slight difference between the two, and I won't go into the details here, but maybe that would be a good subject for another little video. The thing about a catenary curve is the assumption is that the rope has a certain amount of weight per length. So the first foot of rope weighs a pound, and the next foot of rope weighs a pound, and the next weighs a pound, so forth, all the way along the length. So when you look at the middle piece here, we've got, say, 1 foot of rope here weighing 1 pound. And horizontally, that adds up to a pound. That's pretty close to a foot. But if you go all the way to each end, a foot of the length of the rope equaling 1 pound, in terms of a horizontal distance, might only be a few inches. So that's what makes this a catenary curve. Catenary curve is an interesting problem to solve. It's actually not got a direct solution, and you have to go about it in an iterative fashion. That means you have to make an educated guess as to a good, close answer, and then test it out, and you'll find that it's not quite right. You adjust it, and as you adjust the number, you'll get closer and closer, and then you'll find the converge on an answer. I'll show that in the next step of this video. Before we go further with theoretical stuff, I thought I'd just take a moment to point out the appearance of catenaries in real life. This here is a chain hanging between two posts, and it naturally takes on a catenary shape. So there was an architect by the name of Antoni Gaudí working back around the turn of the 1900s in Spain, in Barcelona, and he developed a really cool idea. He realized that he could take chains, hang them from a board upside down like you see in this picture here. You could hang these chains according to like a scale version of some building that he was working on, and it would give him all of these beautiful catenary arches. Now these are all pure tension shapes because that's all that the chain can do is carry tension. But materials like concrete and stone, they're compression materials. they can carry a little bit of tension, but typically concrete, for example, it's only about 1/10 as strong in tension as it is in compression. It's 10 times stronger in compression than in tension, which is why concrete is normally reinforced with steel bars. The steel is there in order to carry tension forces. The concrete itself is really good at the compression. So you can take a form like this, all of these chains, upside down, and you can imagine flipping it over so that it's right side up. And instead of it being tension arches, it would be compression arches. And of course, you wouldn't be using chains. You'd be using something like concrete. So this is exactly what Gaudí did when he designed his church in Barcelona called La Sagrada Familia, the Holy Family Church in Barcelona. He developed all of the pathways, the flow of the lines of structure that you see in this photo here, starting with working upside down with chains and then flipping the whole thing over and substituting concrete for chains. So I think that's a pretty staggering piece of design and a brilliant, simple idea. All right, this video is going to risk becoming a little too long again, so I'm going to break it into 3 parts, not just 2 parts, and this will be the second of 3 parts. But since I've got a moment left here, I thought I would just share with you 2 more pictures of beautiful catenary shapes. This is the famous St. Louis Arch. It's actually a slight variation on the catenary. It is, strictly speaking, a catenary arch, but because the section changes over the course of the length, the weight changes over the course of the length, and the shape of the arch has been adapted to account for that changing section and changing weight. And here's one more for you. This is made of earth, unbaked earth, and it's a material that handles compression very well, but does not handle tension at all, to speak of. These clever folks have figured out how to build these beautiful shapes that are not quite perfect catenaries. They've brought them to a point at the top, which would not happen with a catenary. They've done that in order to facilitate getting the smoke to evacuate out the top. But it's using the principle, using the idea of aiming for a structure that will take on a pure compression under its own weight. So there you go. In the next video, I'm going to look at doing some real math here. And we're going to do a few calculations using this excellent channel I found that has all the catenary math that you could ever want. We will use it to determine how much force the fishing line needs to be pulled in order to get a certain amount of sag, and we will also look at, given the strength of the line, what's the minimum amount of sag we can have without breaking the fishing line. That'll be in part 3 of 3. Hope you come back. Thanks a bunch for following me this long and being patient. If you enjoyed this, please do like, please do subscribe, and as always, I welcome comments. Bye-bye.